To do this one. Yeah. Oh, so you're saying, okay, so you did what? You brought 2x over to the other side. Okay, that's good. That's a good idea. So you're saying, what did you do, essentially?
I added 2x.
Okay, so you added 2x to both sides of the equation. So we have 2y is equal to 2x plus 6. You guys need to be listening to this. Okay.
And then I divided 2.
Okay, so that you're solving for y essentially then, right? Okay. So you divide by 2. Okay. So you have y is equal to, and if you divide both things by 2, you're good as long as you divide both of them by 2. What's 2x divided by 2?
1x.
1x, right? And then what's positive 6 divided by 2? 3. Okay. So you got it in y equals mx plus b. So Tyler was able to see this is a line, but it's not in slope form where we can graph it. It's not in graphing form. So Tyler put it in graphing form. Does everybody understand how you could have seen this as a line? It's degree 1, right? So then you can get it into an equation form, y equals mx plus b form. Now how do you find the y-intercept? It's always when x is equal to 0, right, everybody, for all equations. So if I gave you some random equation and said find the x-intercept, wouldn't you just plug in, or find the y-intercept, wouldn't you just plug in a 0 wherever there's an x? Yeah, so don't forget that. All right, so we're plugging in 0 for x, so we have y is equal to 0 plus 3. So our answer would have been y is equal to 3. How many got it right? Awesome. A lot more better get it right next time, because guys, this was a problem right off the end of level test. Any questions on that? Does it make sense to you? Yeah? Yes.
I tried a slightly different method, which was subtracting 6 and then using the quadratic formula. I got a way different answer than that.
Yeah, good point. So you tried the quadratic formula, but however, this is not a quadratic, right? It's not degree 2. So quadratic formula only works for quadratics. This is a line. So that would be, I mean, nice try. Does everybody understand that you can only use that for a quadratic? Does that make sense? It's not quadratic. Okay. All right, so anytime I ask you, find the y-intercept, you just plug in a 0 for x and then solve for the other variable. Okay, so we're all good with this one. If I put it on the test that's coming up, you're going to get it right. Okay. All right, so let's get going with what we're doing today. So yesterday, we were graphing exponential functions. We kind of focused in on exponentials. One of the biggest things we have to be able to realize is from a parent function, if you're given a new function, what's the shift? So if I give you this parent function, what's my shift looking at this new function? We learned this yesterday. What's my shift from my parent function? F of x is equal to 2 raised to the x, if this is my new function. Okay, so you're saying that whatever's added with x, you go the opposite, so we're going left 2, good. And then what else? Down 1, because that's added on the outside, the sign stays the same. Questions on how the shifting works. You will see these on the test. I'm going to say, what's the shift from the parent function? Just like this. Okay. So just a reminder, anything added with x is you go the opposite of the sign, and then anything added on the outside, you shift up and down. That works the same for all functions. Yes?
Is that from 0, 0?
Yes, from 0, 0. Good question. Okay, here's the parent function. F of x is equal to negative 3 times 1/2 raised to the x. If I said, what's the shift from the parent function? Here's the new function. Where's my shift? Right, just down 7. Is there any shift left and right? Nope, nothing added with x. There is this added on the outside, so that would be down 7. Do you guys all understand what's going on here? So my asymptote would be at negative 7, right? My new asymptote, everybody? Okay. Okay, looking at this one, what's the shift from the parent function?
It's up to or down to right.
Good, so anything added with x is our shift left and right, guys. This is our shift left and right. You always go the opposite. So it would be right too. I'm a little bit concerned that you don't understand what's going on because you're all kind of looking at me with blank stares on your face. Do I need to go into further detail? Like, are you good? What's the problem? Are we all okay?
I think I get it now.
Okay. Anybody have any questions on this? I have no idea what you do and don't understand if you don't tell me. Okay, so let's get going with what we're doing today. So we're just finishing up, getting into more detail with exponential functions, some important things. So first of all, we're going to talk about a special exponential function. Y is equal to e to the x. So common mistake of students at your level is they think this e is a variable, but it's not. If you type in E to your calculator, E is a number. E is approximately 2.72, approximately. So technically we have y is equal to, we would never write the decimal, but really we have y is equal to 2.7 raised to the x. E is just a number. Does everybody understand that E is just a number? Now, if we want to know what E is, let me show you how to do it. So let's type into our calculator. Everybody get your graphing calculator. Notice on the calculator down the one line of buttons on the very left, there's an LN key. Above it, you can see a little e to the x. So hit second LN, so hit second LN to pull up E. Does everybody see E? Now if we want to know what E is, that would be e to the first power. Isn't anything to the first power just itself? So I'm typing in e to the first power, so it's approximately 2.7. Does everybody see how e is literally just a number? Now isn't this just an exponential function? Is it exponential growth or decay? Growth, right? Isn't this our factor? Isn't this our b value? So our b value is 2.7, which is greater than 1, so it's exponential growth. And this is what the exponential function of e to the x looks like. So this is y is equal to e to the x. We have an asymptote at 0, because there's no shift up and down, no shift left and right. And then our initial value is at 1, because there's technically a 1 in front. And then we have 2.7 raised to the x. So our factor is 2.7. So anyways, this is what e to the x looks like. Now, if you want to know what's my function e at 1, wouldn't we just plug 1 into our function like we just did? What if I said, what's my function at 2? Wouldn't you just plug in 2? So what if I said, what's e at 100? What would you do? Just plug in 100. So that's what we're going to do. What's e to the 0 power? 1. E to the first power was 2.7 approximately. What's e to the 10th power? A huge thing, yeah. Yeah, so 22,000. 26.46. So do you guys see how to do this in your calculator? E to the negative 1. So type it in. E to the negative 1. You get 0.3678. So guys, you can always evaluate a function at a value by just plugging it into your function. So that's what I'm going to have you do. So you're doing 14 through 16. So this is a formula you are going to see in secondary 2, and you're going to see it in secondary 3 again. You need to have this down. So now I'm going to give you the formula if you're compounding interest continuously. So understand something, guys. If you go to a bank and you open a bank account, you're obviously going to get interest. One form of interest that they can offer you is compounded continuous interest. So you're going to be gaining interest at compounding continuous means you're getting interest at any second, any time of the day. You're constantly getting interest. And these mathematicians came up with this formula. This is approximately what you earn. And it's this. Y is equal to P times E raised to the RT. So a lot of people call it PERT, just because that helps them remember. So here are the key words. If they say, if you're reading a story problem and it says, how much you're gaining interest compounding continuously. Those are the key words that you have to know. Oh, I'm using PERT. Compounding continuous. This is the only time you'll use PERT. Otherwise, you would not use PERT. So it's y is equal to P times E raised to the RT. So let's think about, so I'm going to tell you what each of these mean. You'll need this. So P is the put down amount, the principal amount. A principal amount is just what you originally have in the account. So it's the initial value. So P is the put down amount, the principal amount. E is just a number. We just talked about how it's approximately 2.7. So the factor they found, these mathematicians, these statisticians that have worked with banks, is that if you're getting interest at any given time of day, at any second, this is the factor of interest you're receiving. It's 2.7. So you're gaining interest at a 2.7 rate, which if you think about it, that's 270% interest, right? 2.7, that's 270, right? Also, R stands for the interest rate. So depending on, so this is the factor, but then they can actually increase that rate by giving you an actual rate. So if you're gaining interest at a constant rate, but you're gaining 8% interest, it's going to be very different than if you're gaining 2% interest. So anyways, R stands for interest rate. And you always have to put it in as a decimal. So if I said to you 8% and you put in an 8, you would be putting in 800%. You can't put in 8. You've got to put in, if I say 8%, you got to put in 0.08. Does that make sense? So you got to put in the rate as a decimal in the R. So if I say 20%, you got to put in 0.20. And then T is the time in the account. So if you keep your money in the account for 10 years, then you're going to have a lot more than if you kept it in for 2. So T is the time in the account. So then, of course, Y is the output. If this is the time you put in, then it equals Y. That's how much you're getting out. So Y is the amount after time, after T time. Does everybody understand that this is the output? This is how much you get out after T time. Yeah? Okay, so you have all these things. If you have all this, all you have to do is plug things into a formula. So it's pretty easy, as long as you know what each of these things stand for. Now understand something. The E raised to the RT part, the R and the T are in the exponent up here. So a lot of people write out PERT wrong. They'll write out PERT, but they'll do something like, they'll go P-E-R-T, but the E part is raised to the RT power. Okay, so make sure even though it's PERT, the RT part's raised in the exponent. Okay, so here's my first example. So it says the bank offers you an interest rate that is compounding continuously. How much will you have in the account after 15 years if you originally put in $200 and you get a rate of 8.2%? Okay? All right, so let's go ahead. Now, here's the key words. If you're reading a story problem and you're talking interest and you don't see the words compounding continuous, you won't use PERT. Well, if you read right here, do you see the key words? Compounding continuously. So we say, okay, I'm using PERT. So I'm going to write that down. We know that PERT is Y is equal to a P times E raised to the RT, PERT. Then you have to know what each thing is, and you're just plugging it in. So we have Y is equal to P. P is the put down amount. Didn't we originally put in $200? So our P is going to be $200. Is everybody comfortable with that? So I've taken care of that. And then E is just a number. So we have E, that's our factor. And then our rate of interest. We're getting an 8.2% interest rate. We have to write that as a decimal. So 8.2%. If you don't know how to change that to a decimal, what you'll do is take the decimal, move it back 1, 2 places. So the decimal for R, for 8%, 8.2% is 0.082. Does everybody understand how to do that? That's your R. And then time in. So that's R times T. The time in the account is 15 years. So 15. Now it's just typing it into your calculator. So you'll hit 200. And then second ln, because that'll put E in your calculator. And then 0.082 times 15, close your parentheses. So the amount in the account after 15 years is $684.25. So that's how much money you have in the account after 15 years. So you went from $200 to $684 with that interest. Isn't that pretty good? I mean, that is 15 years that you can't touch the money, but you earned that for doing nothing. Questions on that? Pretty easy, right? Any questions? Okay. So, these are the problems you're doing. Stay with the problems I'm assigning right this minute. 7 and 18, 20, 24 through 25. Ready, set, go. Okay, so everybody, you need to pay really close attention to this. I don't really know how other to teach you than this way. I know there's a way. I'm going to have to research it, but hopefully this will make sense to you. But you need to pay really close attention because people start to confuse it with some things. So it says, how long will it take you to triple your principal amount at an annual interest rate of 6% compound continuously? So things to notice about this problem. Do you see the words compounding continuously? Yeah, so that's when you know I must be using PERT. So I'm going to write that down. We know that the equation for PERT is Y is equal to P times E raised to the RT. Questions on that? So now it says, how long will it take you to triple your principal amount? So do we know what our principal amount is? No. But we do know that whatever that amount is, we're going to have it tripled, right? So I'm going to just say, what if I put in 1? What's triple at? 3. So if I put in $1, it's going to be, by tripled, it'll be at $3. Does everybody understand? Now it says, how long? Won't we be looking for T? Isn't T how much time? How long? And then we were given the rate, right? 6%. So let's plug in everything we know. We know the amount in the end. Isn't 3 what we are getting in the end? Okay, so we know the amount in the end is 3 will equal to, our put down amount was $1, And then we have E. You just remember our rate is 6%. We always write it as a decimal, 0.06, and then times T. Now looking at the equation here, we only have one unknown. It's T, right? So now we just have to algebraically solve for T, and that's how much time it will take for it to triple. Now notice, I promise you, if I would have put in $2, what's triple that? 2, 4, 6, right? Wouldn't that be triple? So if we use 2 and 6, we're going to come out with the same answer as long as you set it up correctly. So what if I said, how long will it take for you to double? You'd use 1 and 2. That's just some good examples, okay? So now we're solving for T, but notice something. This is the important thing. Do you see how T is in the exponent? Okay, you got to be really careful about how you get that out of the exponent. So in secondary 3, you learn this in very much detail. I really can't figure out any other way to do this one without showing you how to do it this way. So pay close attention. So first of all, algebraically, we're going to try to get T alone. So the first thing we take care of is this multiplication. So to get this 1 to go away, won't we divide both sides by 1? Yeah? So then we have 3 is equal to E raised to the 0.06 times T. Now a lot of students think at this point they can divide by E, but that's not true. T is not being multiplied to E, right? T is in the exponent. So you've got to bring this down out of the exponent. The only way to do that, way to bring something out of an exponent is to apply the inverse. Now I'm going to tell you, the inverse of the base E is ln. So once again, the inverse of the base E is ln. So we've got to apply the inverse to both sides of the equation. So the inverse of E is ln. So we're going to take the ln of both sides of the equation. Ln stands for natural log. So we're taking the ln of both sides of the equation. So on the left, I have ln of 3 is equal to, now ln and E, they do undo each other. They're inverses, so they cancel out. And then this can now drop down. So this drops down to be 0.06 times T. Does everybody see how I took care of E? I isolated E, then I took the ln. ln undoes E. So E undoes ln as well. They're inverses. Just like addition undoes subtraction, ln undoes E. Now look right here. To get T alone, isn't it multiplied to 0.06? What undoes multiplication? Division. So now we'll divide both sides by 0.06. Divide by 0.06. So now we have T alone. And there's going to be the time. So type it into your calculator. There's an ln button. So you'll type in ln. It's right above. It's the E key, but it's just the ln. You don't have to hit second ln or that will put E. So you hit ln of 3. Close your parentheses. Then divided by 0.06. We get 18.3, right? 18.3. So guess what? It took 18.3 years for my put down amount to triple. Does that make sense? So like let's say that you put in $500, to get triple that, you would know it's going to take you 18.3 years. Does that make sense, everybody? Is everybody good with that? Because that was kind of a brand new example. Okay, so then do the 19 and 23. Ready, set, go. So once again, on number 19, how many of you got 9.9 years? That is correct. Now understand something, at this level and on an ACT for sure, you'll all want to pay attention. They would never write this as an answer. So that is definitely 9 years, right? Everybody? So we know it's 9 years for sure. But now we have 0.9. Are we talking in per year? So if we have 0.9 of a year, that's 90.9. Doesn't that mean 90% of a year? Everybody. Okay, so you'd have to say to yourself, how many days are in a year?
365.
There's 365 days in a year, right?
366.
So you would do what's general on ACT. So it's generally 365 days is a year. So how many days in 90% of that? So you'll take 365 and multiply it by 90%. So 0.90. What do you get? 365 times 0.90. 328.5. So 328 days. Does everybody understand that? So it was 9 years, and then 0.9 of the year was 9 years and 328 days. That's how long it took for that amount to double. Does that make sense, everybody? So on that 28th day, on that 328th day of that year, of that almost 10th year, after 9 years, that's when you reach the double the amount. So I'm just telling you that so that on your ACT you can get it right. Does that make sense, everybody? Yes? Okay. Then you could even get more specific because you could go through and say, okay, but we won't do that. Anyways. Okay. Next thing. Here is the formula for half-life. You need this. So this is the formula for half-life. A is equal to A naught times 1/2 raised to the t over h. Now this is just an exponential function. That's why all of these, E is just an exponential function. This is just another exponential equation. So this is the formula for half-life. Once again, A is equal to A naught times 1/2 raised to the t over h. Or we could write Y is equal to A naught times 1/2 raised to the t over h. So this is just the same as pretty much, a little different as PERT, because this stands for our initial value, initial amount, or our initial value, or the put down amount, or how much you begin with. And then the 1/2 is just the factor, just like E is our factor. Does that make sense, everybody? And then raised to the RT, this is raised to the t over h, where t is the time in, and then h is the half-life. So h is the half-life. You've got to know it's t divided by h. T is the time in, and h is the half-life. And then obviously, it equals A. This is the amount after that time in. So this is the amount in the end. Amount after the time in. So get that formula down, then I'll just give you an example, and then we'll be able to finish up the worksheet. So this is just an exponential function. Does everybody see how it's just an exponential function? It's just kind of fancy. Okay, so it says potassium 12 has a half-life of 25.13. Now this looks hard, but it's really easy, so don't get caught up in the wording here. So it says potassium 12 has a half-life of 25.13 hours. So I'm going to write that down. Our half-life is 25.13. So I'm going to write H is equal to 25.13. Does everybody understand how it just reads exactly as it is? It gives you the half-life. Yeah? Okay. Now, this is what people get confused with. They're like, when am I going to use that 12? Well, we're not using that. The name of what we're looking at is potassium 12. So don't get caught up in that. So we have potassium 12 has a half-life of 25.13 hours. After that time, potassium 12 will have decayed. So we know it's exponential decay. Find the amount remaining in a 9 milligram sample. So how much did we originally start with? 9 milligrams. So A naught is 9 milligram sample. And then it says after 16 hours. So the time in is 16 hours. So now we're just plugging it into our formula, which was this. So we have A is equal to, or Y is equal to, either way works, the initial amount, which is A naught, so 9 milligrams. Then we know it's 1/2 raised to the T over H. So the time in is 16 over H, which is the half-life. The half-life is 25.13. And then we're just typing it into our calculators. That'll give us how much of milligrams is left of our sample after this amount of time in. So you'll type it in 9 times 0.5 raised to the parentheses. 16 divided by 25.13.
5.78.
So 5.8 milligrams. So the amount in the end after 16 hours, wasn't it hours? Yeah. Is 5.8 milligrams. So it started at 9 milligrams and it's after 16 hours at 5.8 milligrams. So not hard, but you have to know what you're doing. Okay. Okay. Questions on how to do that? Make sure you put this in your calculator in parentheses. All right. So now you can finish the worksheet. And it is due at the end of the hour. You have 20 minutes. Finish it and hand it in at the end of the hour. That's due along with properties of exponents review. It's an 8A.